So we have seen that maps on fundamental groups give you maps between Eilenberg-MacLane spaces. In fact, even more than that, all you need is the target to be an Eilenberg-MacLane space. And indeed, we'll see next that these are unique. Okay. So again, let our y0 be a KG1. Okay, and x path connected. Oh, let me stick to the previous notation. Let's call this x0 be a KG1, and we have y path connected. Now suppose we have fg, both of them map y and some point y0 to xx0. And suppose we know that f star equals g star as maps on fundamental group. Yeah. Well, then f is homotopic to g. The converse is also clearly true. That is, homotopy equivalent homotopic maps induce the same map on fundamental group. Homotopy fixing base points. So in fact, this is fixing base points. Yeah, and we'll see a consequence of this for homotopy equivalence as between two spaces, both of which are KG1s. Okay, so this is the result, and proof is we define H, which one should remember the domain space is Y, so 0, 1 to X, extending. Well, what all do we already know? We know H on the base, H of X 1 at the base 0 is f of, let's call this Y not X. H of Y0 is this, and H of Y1 is going to be g of y, and at all base points, so if I'm looking at the base point which I call y0, s is going to be equal to just the base point, which is x0. This is for all s in 0, 1, and in both these cases for all y in y. So we have a homotopy. It's determined on the top and the bottom. Okay. And we want to define it on the top. Okay, so we do this cell by cell. Rather, yeah, cell by cell. I could say cell by cell in each dimension inductively on dimension. But 0 dimensions we have to do nothing. Okay, so extend to y of y cross 0, 1, the one skeleton of this product space, which is a CW complex as we observed at the other way. The 0 skeleton, already the function is defined because any vertex is either in the base or on top. Okay, 0, 1 by the way is a cell complex with two vertices as usual. So we have taken the product decomposition. Okay, so this means that we have, and what are the new cells here? There are cells at the bottom on which we have already defined it. Okay, so there's the bottom here. We have cells on top sitting above on which again this is already defined. So let's draw a little bit of it, and this may be let's keep it a little straighter. This might be y0 on which it is already defined. Okay, but where we have to define it is on these kinds of lines. So let's have them in purple. So a line like this. Okay, and even so, and already we have two kinds of edges below, those that are part of the maximal tree, which here is black, and those that are not. Here they are blue. Okay, so that will become important when we define it on the 2 skeleton, because on the 2 skeleton there are two very different kinds of edges. Okay, so you remember now that if I have any vertex v, so T is again as usual a maximal tree, and xi v reduced path from the base point y0 to v. Okay, and what do we have to connect? If I have a point v, so this guy goes to f of v and this guy goes to g of v, and I have to find a path from f of v to g of v. I could find an arbitrary path, but that would be a bad idea because then we'll lose control about higher extensions. Instead, we do have a path, okay, more or less canonical, which is that I have this path xi v which connects this guy. If I apply f to that, that's a path from f of y0, which is the base point x0. Okay, so this maps to x0. This also is y0. This also maps to x0. So I can follow this path, and then I follow g of v. Okay, and I can use that to define the map here. So let's be concrete here. So we extend to v cross 0, 1. This is an edge by using the map xi v. Well, not that. I apply f of xi v bar star g composed with xi v. No, and I said v, but of course we know what v is. Oh yeah, it is v. It's the v, which is this vertex. So this is e. So xi v composed with xi v. Again, to clarify, what I'm saying is that remember the edges of the product are going to be the edges. In this case, this is a 0. This is edge. The whole thing is an edge. So this is an edge of 0, 1. Indeed, it is the edge of 0, 1. And this is a vertex of y. So that those are 1 cells that we have there. The other 1 cells are the ones that are already either at the top or bottom. So for those, we have already defined the map. So we define extend to v cross 0, 1 by this. So we can, and this extends to the 1 skeleton. Okay, and now since we have this picture, it would be kind of nice to just do it here. Let's extend across such cells as well. Okay, so suppose we are given E in T, so it's an edge, so it would be more accurate to say it's contained in T rather than belongs to T. Given edge contained in T. Okay, so now we are extending across the 2 skeleton. So we extend to E cross 0, 1. Okay, so now let's see what we already have here. So we have a path here, and we have these 2 paths which were described in purple. Then we have the path here. Okay, so this guy maps to f of e. This guy maps to g of e. And without loss of generality, let's say e is picked this way so that the base point, which is in both these places, this is the same base point. This is what we'd call y0. So we have xi v here. Okay, so what we know is that this path here, by definition, has gone to f of xi v. Let's write it larger by pointing to this. F composed with xi v bar star g composed with xi v. We have done all this once before when we showed trees were contractible. It's exactly the same calculation. And on the other hand, on this path, so this is f composed with xi v star e bar star g composed with xi v star e. Okay, so what that tells you is the following. What that tells you is that if you follow this loop around, you get the identity. I mean, this is homotopic to the identity. So boundary is homotopic to the identity. As I said, this is the same calculation we have seen before. So this is going to be, if we went down this way, it would be the opposite of this, G O xi v and F O xi v. So G O xi v bar and then F O xi v. We followed this, we'll pick up an E. but then we look at f of xi v star e bar, so that gets cancelled by the halfway point. Then we pick up a g o xi v and then get rid of the e when we come here, and the final half getting us back was the identity, was the one we picked up before. Okay, so this is the same calculation as in the tree, and so we extend. Okay, this is nice, but this came like the contractibility of the tree from the fact that we chose in a canonical way following f and g. This leaves one more case for which we'll look at a slightly bigger picture, and it's related to the same thing, which is these blue edges. This is in E, which is not in the tree. Okay, so crucially you notice we have not actually used this hypothesis f star equals g star. We'll use that when we extend to the tree. Okay, and exactly there. So let's again look at the picture. Let's make it big and recall that. So we have an edge which previously was color coded as blue to emphasize that it was not in the tree. So I have the edge E and I have the edge E. Okay, and so you remember that we had associated to this path mu E, which was psi v, exactly the same thing, but psi E of 0 star E star psi E of 1 bar. Okay, so we had this loop, and this was a generator of fundamental group of pi 1 of the appropriate space, in this case yy0. Well, the one skeleton of yy0. It's also the generator of the full fundamental group, but it's a generator in the strong sense of it being a free group on these generators. Okay, so we had the purple sides. And now let me emphasize the halfway point. Okay, so the halfway point here, this was f composed with, so if I'm going up, this was f composed with xi of 0 in the up direction. So I'm going to just change the direction and go down here. It's not xi of 0, xi e of 0. So I had the path which went along the tree, and then I went up. As I went up, I took the reverse of that path. So as I go down, I have this guy, and this is g composed with xi e of 0. Okay. Similarly, here we have paths. This is f composed with xi e of 1. By the way, I've assumed that e of 0 is where the first point you encounter as you reach this edge along the tree. Otherwise, you just reverse e and e bar. So that will change the notation a little bit, but no essential change. So here we have g composed with xi e of 1. Okay. So we are almost there actually, because you see these points, remember the reason I wrote the midway points is these points actually map. Yeah. So this is under the map what I have written here. These points map to the base point x0 in both cases. Base point of the Eilenberg-MacLane space. And so what happens to this path? Well, you see this is f acting on this guy. This is f of e. So I should say f of e here. And this guy is g of e, this is the edge e, followed by this, which is simply f of mu e. And the upper path is going to be g of mu e. Okay, and these are now the base loops. Okay, so we know f star equals g star. So this is our hypothesis. Hence f of mu e, or more accurately f composed with mu e. Okay, so this is, I could write this as f hash of mu e or something, g hash of mu. So this whole thing is homotopic to g composed with mu e. But now we have in one direction f composed with mu b, hence the boundary is homotopic to the identity, that is, or rather hence the map on the boundary, for which I did not introduce notation, extends to D2. And indeed we have taken care of all kinds of 2 cells, because 0, 1 has no 2 cells at all. So that leaves 2 cells which are completely in the space which we had, which is our domain Y, cross 0 or cross 1. So on those the map was already defined, or 1 cell cross 1 cell, and we took care of the 2 1 cell cross 1 cells, one of them simply by careful definition, but the other by the hypothesis. So the hypothesis told us that the maps are equal on mu E, and hence, I mean, they're equal on fundamental group, hence they're equal on mu E, and hence we get an extension on this 2 scale. So now we are in wonderful shape, because we can extend to Y3, Y4, etc., using simply the fact that pi n of x, x0, is 0 for all m greater than or equal to 2. So now we are exactly as we were in the previous case. Okay. Hence we can construct a homotopy between f and g as soon as the maps agree on the fundamental group. Okay, a corollary to this is a very nice theorem with which we almost end this section. We have only one more task to go in this section, which is to show k pi 1s actually exist, and that is relatively easy. So let's take x and y are so let x, y be Eilenberg-MacLane spaces. With some hypothesis, base point. Okay, then x is homotopic equivalent to y if and only if we have pi 1 of x, x0 equals pi 1 of y, y0. And there is more here, that is maps, group homomorphisms correspond bijectively to maps up to homotopy. The entire homotopy theory is the group theory. This has many nice consequences. It lets us define group cohomology and group homology by reversing. Given a group, you pick the Eilenberg-MacLane space and you know that is unique, and various other such applications, more sophisticated constructions of that nature. But so topological properties, at least of the homotopy type of X, are now properties of the group. So this is very significant, and it's very nice. But also, just to appreciate, I had early on in the course emphasized that algebraic topology goes only one way. It can tell you spaces are different, it can't tell you they're same, even up to homotopy. It cannot tell you that, it can tell you maps don't exist, it can't tell you maps exist. Now, so this Whitehead theory was complementing algebraic topology. It's a kind of geometric topology. It's telling you maps exist given them algebraically as continuous maps. It's telling you spaces are equal, at least up to homotopy given these. What is more normally called geometric topology involves refining from homotopy equivalence to homeomorphisms and diffeomorphisms, but the spirit has a lot in common with Whitehead's theory. We continue to use decompositions instead of into cells, into handles or some such thing. Okay. So we just have one last task in Whitehead theory, which is to show that these KG1s actually exist, and given the work we have done, that is fairly easy.